Hi everyone, welcome to the last video of chapter 6. Today we're talking about linear combinations and how they form spanning sets. So first of all, let's define what a linear combination is, and then I'll talk about what it means that it is a spanning set. So if you have two non-collinear vectors, u and v, a linear combination of these vectors is if you take any scalar a and multiply it by u, plus any scalar b and multiply it by b. Okay, and I'm just going to clarify that a and b are scalars by saying they're in the set of all real numbers. So really, it's taking those two vectors and adding them together, but it can be shorter or longer versions of those vectors to create one single resultant vector. So remember that u is a vector, v is a vector, and then AU plus BV would be one vector. It would be the resultant vector of the sum when you multiply U by A and V by B, and then you add those two vectors together, you would get one resultant vector. So the vector AU plus BV is the diagonal of the parallelogram formed by the vectors AU and BV. So for example, if you have U, so you can see my scale here. If you have u as -1, 2, okay, there is u. And v as 2u, and v as 1, 4. So 1, 4. Okay, what would 2u minus 3v be then? Well, 2u is 2 times -1, -1, 2. So that gives us -2, 4. So the vector 2u then is -2, 4. So it's in the same direction as u, should be right on top of it, but twice as long. And then -3 times v is -3 times 1, 4. So it is -3, -12. The coordinate. So -3, -12. So it'd be about here. Okay, so that is -3v. So it should follow exactly in line with v. It's just in the opposite direction and 3 times as long. So the resultant vector then, I'll do it in green, would be 2u minus 3v. So it would be -2, 4, plus -3, -12, since I already did the subtraction by making this negative. So you get -5, -8. And you'll see when plotting this, here is our resultant. So this is the linear combination set out. And you'll see that it is the diagonal of a parallelogram that could be created here. Sorry. If I had done this properly and to scale, then this would be the diagonal of the parallelogram formed by these points. Okay, so that's the resultant -5, -8, and that is 2u minus 3v is that green. Okay, so that is a linear combination. So basically you're taking two vectors as they are, and then you can multiply them by any scalar to make them longer or shorter, or even in the opposite direction and longer and shorter. And then you're creating a single resultant out of those two vectors by adding them together. So every vector in R2 can be written uniquely as a linear combination of the unit vectors. Okay, so that means basically if you take any vector, I can kind of write this on the side, sorry. So if I take any vector I want in R2, so let's say like 4, 10, I can write it as a linear combination of the unit vectors. So that would be like the vector 4, 10, so let's call this u. U can be written as 4 times the unit vector I plus 10 times the unit vector j. And this exact thing can be done for any vector in R2. So the unit vectors are I, which is 1, 0, and j, which is 0, 1. So what we say is that I and j span R2. So that means that a linear combination of I and j can be made to represent anything on the xy axis. So what I think about with span R2, it's because those two vectors can represent anything in this whole R2. So they span R2. So another way of saying that is that the set of vectors I and j form a spanning set for R2. Okay, so that hopefully makes sense to you because any vector can be written as a combination of two other vectors. But what's a little bit harder to understand is that any two non-collinear vectors in R2 also form a spanning set for R2, since I and j could be used to represent those vectors. So there are an infinite number of sets that span R2. However, 0, 0 cannot be used as one of the vectors, the 0 vector. So every vector in R2 can be written as a linear combination of any two given vectors that span R2. Okay, so algebraically we can do this as well. So demonstrate that u, so 423, can be written as a linear combination of these two vectors. So we have these two vectors and we want to create some coefficient on each of them so that when you add them together, you get 423. So this means that we want to make this a true statement. So some coefficient a in front of negative 1, 4 plus some coefficient b in front of 2, 5 equals 423. So now we just need to find the a and the b that satisfy this equation. So this would mean that we'd have negative a, 4a plus 2b, 5b equals 423. So from this, we can create two linear equations, okay? So the x's would have to add to 4, and the y's would have to add to 23. So now this is just a grade 10 linear relations question. So you can use substitution or elimination. So I use substitution. I just rearrange this to be a equals 2b minus 4. And then sub that in to the other equation. Okay, and then you simplify and collect like terms, and you get that b is equal to 3. And then you can sub that back in, and you get that a is equal to 2. So therefore, the linear combination that works is if you have 2 times minus 1, 4, plus 3 times 2, 5, that gives you the resultant vector 423. Okay, so this same process can be done to create any vector u, which is why these two vectors span R2, because these two vectors can be used as a linear combination to create any u that we want. It's just the coefficients that will change. Okay, example 2 is a little bit more onerous. We have to actually prove that these form a spanning set for R2. So what that means is that these two vectors actually can create any vector that you want in R2. So this means that we would have some a value in front of 2, 1, plus some b value in front of minus 3, minus 1, to create any vector x, y in R2. So let me explain this underneath. So this here is what we call a linear combination of the given vectors. Okay, and we're using this to represent any vector in R2. Okay, so that's what's going on with that. So now we have then 2a minus 3b equals x, and a minus b equals y. So I just distributed the a and the b through the brackets, added the x's together to get the x, and the y's together to get the y's. Okay, so from here, we can do some elimination. Okay, so I'm going to leave the 2a minus 3b the same, but I'm going to multiply the second equation by 2, okay, to get 2a minus 2b equals 2y. So now when you subtract one equation from the other, the a's cancel out, and I get negative b equals x minus 2y. Now, if you arrange this, you get that b is equal to negative x plus 2y. All right, so now let's put this b back in. So remember now a can be written as y plus b. So that's just rearranging the second equation. So a can be written as y plus, and instead of b, we can put minus x plus 2y. So a can be written as 3y minus x. So what have we actually done here? Well, let's remember a and b are the coefficients in front of our two given vectors, and x and y are the resultant vector that we want. So these two formulas allow us, when we know what resultant vector we want, we simply plug in the value for x and the value for y, and then we can solve for what those two coefficients are to give us that resultant vector. So this proves that no matter what x and y are, there is an a and a b that can be found to create a linear combination for that resultant vector. So any vector in R2 can be written as a result. So let's summarize that. So now, when we are given any vector in R2, we can find values for a and b using the x and y coordinates. So let me do a quick example to show what I mean. Okay, so let's say, for example, we want negative 3, 7 to be written as a linear combination of the given vectors. Okay, so that's the 2, 1 and the negative 3, 1. Well, then we put, this is our x, right? And this is our y. So now we just put that in. So a is equal to 3 times 7 minus 1. So our a value is 20. And b is written as negative 3 plus 2 times 7. So that gives us 17. So the linear combination that works then is 20 oh, sorry, this should have been minus, I made a mistake here. X is negative 3 minus negative 3. So this should be 24. Sorry, my mistake. Okay, so our a value is 24. So we have 24 then times vector 2, 1 plus 17 times vector negative 3, negative 1. That will give us the vector that we want, minus 3, 7. So this process can be done for any vector in R2, anything, any vector. So that's why it means that these two given vectors span R2, because you can create a linear combination to come up with any resultant that your little heart desires. Okay, so the similar thing can be said in R3. Okay, so first of all, the set of the 3 unit vectors is the standard base for R3. So every vector in R3 can be written as a combination of I, J, and K. Where's my little thing there? I, J, and K. However, there is an infinite number of sets containing 3 vectors that could also be a basis for R3. So in R3, any 2 non-zero, non-collinear vectors span a plane. Okay, any non-2 non-collinear vectors span a plane. If OE lies on that plane, then the point E lies on the plane. So when 2 or more vectors lie on the same plane, we call them coplanar. So what that looks like, so we represent, when we're drawing planes, we represent them with a parallelogram. Okay, so we can draw vectors on this plane. So like O could be here. Okay. So OB, OC. So these lie on the plane, and then they can create the resultant vector OE. Okay. So then if you have other vectors like here, if I create OD, I can say that vector OD is some M times OB. Or I could say that, here's our A, I could say that vector OC is some other N times OA. Okay, and then OE is a linear combination then, MOB plus NOA. Okay, so these are all coplanar because they lie on the same plane. All right, so example 3 is determining if C lies on the plane determined by these other 2 non-collinear vectors. So if it's true, then a linear combination will exist so that A and B equal C. If it's not coplanar, there will not be a linear combination possible to create C given A and B. So we're going to test to see if this works. So in this case, because the vectors are named A and B, we're going to call our coefficients M and N. Okay, so we set up a linear combination of the given vectors. So M in front of -1, -2, 1, and N in front of 3, -1, 1. And we're going to say, can we find an M and N so that there's a linear combination that equals C as required? Okay, so that sets us up with 3 equations. -M plus 3N equals -9. -2M minus N equals -4. And M plus N equals 1. So we'll call these equations 1, 2, and 3. Now we're going to solve any 2 equations. So I'm going to look at equation 1 and equation 3, and using my wonderful mathematical skills, I'm going to solve them. So when you solve them, you can use elimination because they're stacked, right? So right away you can see you get 4n equals -8. So your n equals -3. So therefore then for m and n to equal 1, your n equals -2. Okay, simple division. So then m would have to equal 3 so that it satisfies 1 and 3. So these are the solutions based on the 2. But now I want to see, does m and n hold in the 3rd equation? So in this case, do they satisfy 2? Okay, because these m and n will solve 1 and 3, but does it work in the one that I didn't do? So when I say 3rd equation, I don't necessarily mean equation 3. I mean the one I didn't use in step 3. So when I put in -2 times 3 minus -2, I get -6 plus 2, which is equal to -4. So yes, that works. It satisfies equation 2. So because that's true, C, so since3A minus 2B equals C, C lies on the plane determined by A and B. Okay, because a linear combination exists for this to be true, then it does lie on the plane. Okay, parts B, does this lie on the plane? So notice that our X and our Y value are the same. So our step 1 to 3 would be the same. But when we get to step 4, we would get -4, which doesn't equal the Y value of -5 like it's supposed to be. So we would say that C is not coplanar with the plane determined by A and B. Okay, because a linear combination wouldn't be possible for all 3 points. Okay, so this is an algorithm. The steps are set up. So when you're doing your homework, feel free to follow the algorithm until you're comfortable with it and can learn it and hopefully understand it for the test. But I tried to lay it out for you kind of simply so you can hopefully understand why each step works. So thanks for watching, guys. Hope you learned lots.